It's office hours, mathematicians. Office hours in my actual office today. Wow, magical, absolutely magical. Um, yeah, let's yap about some random graph theory stuff again. Probably we'll talk about some graph theory. Yeah. Got a train of thought to wrap up from yesterday, magical. I suppose.
Absolutely.
And yeah, we're talking about root lattices. We're talking about star-closed sets of vectors. Good morning, Kostaka Corey. And we're talking about line graphs. That's what we're talking about. So let's go revisit our friends, Godsill and Royal. Shall we? See what they've been up to. Where were we, like 256 or something? I guess we should probably look at the table of contents. Reorient ourselves here. Somewhere around 256. Yeah, indecomposable star closed sets. Maybe 270? Maybe 270, was that it? We left off on some interesting lemma. I remember that much. Yeah, by the way, the enter button, the number of buttons on my keyboard have been kind of sticky lately. I don't know if that's like what food debris have gotten in it or something. I don't know. Maybe I need to get some keyboard cleaner. But this has never happened before with any other laptop. So I really hope it's not just a deep hardware issue. Hello, Lock. Hello, Lock. I tried reinstalling drivers. A generating set. Yeah, I think this is where we left it off. 12.4.3. If we have a graph with minimum eigenvalue at least 2, then the star-closed set of lines is indecomposable if and only if X is connected. That is pretty cool. Wait a second. Did we cover the fact that for such a graph, how is it possible to play live stream on 2 times speed? Maybe there's some weird lagging type stuff going on. I don't know. Maybe you did time travel a bit. Wait, I feel like we missed something about... I feel like we missed something here. The set of lines spanned by the vectors in Dn is indecomposable. Now suppose... Oh, right. I think this is this... hello, how's it going? Hello, L. Today's going to be short, by the way. I got a tutoring session in like 25 minutes, so I'll probably peace out in 20 minutes. Suppose that X is a graph with minimum eigenvalue at least 2. Right, we were looking at this yesterday. And this is the Gram matrix. Oh, right. Okay, so we argue that this is the Gram matrix. And we define Lx to be the star closure, right? Okay. Now I am happy. So first suppose X is connected. L prime be the line spanned by vectors whose Gram matrix is this. Lines corresponding to adjacent vertices are not orthogonal. Okay. Okay, if you say so. Lines corresponding to adjacent vertices are not orthogonal. If you say so. You couldn't find much on 2-category theory textbooks/notes yesterday, but you did find a bit on higher category theory. Interesting. What about bimodules? Did you look up the category of bimodules? You should go look up the category of bimodules. Yeah, possible to play live stream 2 times, yeah. If you're not off by more than 2 seconds, yeah. Man, I'm tired. I didn't follow my usual routine this morning. Mind you, I say I'm tired most mornings. Yeah, lines spanned by the vectors. Lines corresponding to adjacent vertices of X are not orthogonal. Why would that be the case? Why would that be the case? Carradine has an ebook which has higher category theory. Yeah, but I think specifically Locke wants 2 categories. Specifically. I mean, isn't Carradine Lurie? I know other people are involved. I know what you meant, Al. But okay. Why would adjacent vertices not be orthogonal? Like, I mean, what if we took the matrix for this graph, yeah, why? Unclear to me. Well, what's the inner product gonna look like? They'll have ones. A number of ones for their number of common neighbors, right? So 2 columns, the dot product of 2 columns will be equal to what am I trying to say here? I mean, this is the sum over all the vertices W. All the vertices W where W is adjacent to both of these things. Right? And so Locke, because the category of bimodules is a 2 category. That's how it's going to teach you. It's everyone's favorite example of a bicategory. So there you go. So U dot V. Yeah, the brain isn't braining this morning. You meant 2 category. Yeah, it's a. But that's like it's the quintessential example of a 2 category. So, undoubtedly, sources that talk about the category of bimodules are going to most likely say something about 2 categories. And even if they don't, just go get a handle on that, and then it will be very easy to work out stuff about 2 categories for yourself. It's like you learn about the real numbers before you learn about fields. But also, I'm confident that if you find the right source on bimodules, they'll talk about the two categorical structure of it. Or maybe they'll talk about bicategorical structure. Again, there's some difference between strictness and not, and I don't remember. I don't remember which is which. Well, actually, okay, sorry, you're right. Actually, you're right. The most standard example is the two category of categories. You're absolutely right. Yeah. Yeah. I mean, did you try looking that up? If you try looking up the two category of categories, things a gibbing. Yeah, well, us up here in the sunny beaches of Canada are living in the future, compared to you Americans dwelling in the past. So our Thanksgiving happened quite a while ago already. We were thankful long before you guys. Okay, what's going on here? Why can't these be orthogonal? If U and V are adjacent, I don't get why this would be the case. Banned from stream for not gibbing? You don't have that power lock. Yeah, Leo could Uno reverse it. Corresponding to adjacent vertices are not orthogonal. Man. Okay, what if I removed one of these? Would it become clear? Let's say 2 and 3 aren't adjacent now. Is it still clear? I guess it's still clear. You didn't pay attention to stream at all yesterday? What are these lines? Which lines? The lines they're talking about here, or the lines that I've drawn? This is just a graph. So let's see. I mean, why? Wait a second. Now they've done this. Hang on. Did I draw this? I mean, this should be a line graph, right? This should be the line graph of the 3 path, right? Because it's like boom, boom, boom. Yes, so this should be a line graph. Maybe there's a restriction on the vertices. It should be a line graph, so it should have minimum eigenvalue at least 2. One. The lines they're talking about are lines in Rn, in our case R3, which are spanned by... wait a second, but it's the Gram matrix. Lines corresponding... I need to be... this is a claim about... I see, this is a claim about the Gram matrix, not the adjacency matrix. So the Gram matrix is U such that this is true. Okay. But now how do I reason about that? How do I find the... What's the constructive process by which one finds a Gram matrix? Let's go back to positive semi-definite matrices. Yeah, how do we find that UUT? Something about diagonalization, something, eigenspaces. Here we go. Hermitian. No, we don't want Hermitian. We want the real version of this. Oh, well. Oh, when n is real. Okay. If and only if such a decomposition exists. More generally, do I mean Graham-Schmidt? No, I don't think I mean Graham-Schmidt. Oh wait, maybe you're saying, yeah, I don't know. Apparently, you can buy YouTube Premium to play stream at 4x. That's some serious time traveling. Do it. Report back from the future once you did it. Okay. Right. Take the eigen decomposition. So we can define D1 half as the diagonal matrix whose entries are non-negative square roots of eigenvalues. Then, so B is D1 half times Q. Right. Right. So the point is, where'd I put my writing thing? So the point is what? Let me give this a new name. I'm gonna call this thing B. So then we know that we can go, let's say P inverse P, B, we can diagonalize it, and then I guess we define U to be like D1 half P. Then has an eigen decomposition. D is a diagonal matrix whose entries. Yeah. Let's see. The matrix P. It's got to be something to do with the matrix P, though, right? So, like, are the columns of P should be orthogonal? But no, not necessarily in general. We're just saying adjacent vertices. Adjacent vertices should. I don't know why. Whatever. Let's move on. Let's just move on. Lines corresponding to adjacent vertices are not orthogonal. Yeah. Yeah, but why? Why would that be the case? I mean, I think it would be enough since it's yeah, I don't know. Oh, wait a second. I think I can get it because it's right. So if our vectors are v1 through vn, then the inner product of vi and vj is actually the ijth entry of a plus 2I. You can't help because you have no idea what these lines are. These lines are so x is a graph. We look at, it's a graph whose minimum eigenvalue is at least -2. So then you look at the adjacency matrix plus twice the identity matrix. This turns out to be a positive semi-definite matrix, and so it can be realized as the Graham matrix of a set of vectors in Rn. And so we're looking at the spans, the lines given by the spans of those vectors, and then we take the star closure. But maybe those words don't mean anything to you either. Right, so hang on. So this will be equal to, so they're not orthogonal if this matrix, if they're adjacent. Well, this is equal to Aij well, forget the diagonal doesn't matter. So this will be 0. So this is just equal to aij. Right. And then it's equal to 1 if they're not adjacent. Okay. Yeah, we got there. It's actually easy. 100% that's a coincidence, Locke. 100% that's a coincidence. 3,000 million billion %. A trillion %. Infinity %. Actually, I mean, I don't know. If any two things involve the number 2, I mean, technically that's not a coincidence because they're both like logically connected to the number 2, but maybe not a deep and meaningful thing. So what does line correspond to adjacent edges mean? I don't understand your question. What does line corresponding to adjacent edges? Oh, because we have one vector for each. We have one vector in the space for each vertex of our graph, right? And to say that A plus 2I is the Gram matrix is precisely to say that there exists n vectors in Rn whose matrix of inner products is given by A plus 2I. And so the claim is that these vectors will not be orthogonal when vertex I is adjacent to vertex A. And we can see that because if vertex I is adjacent to vertex A, then Aij will be equal to 1. So the inner product will be 1, so they won't be orthogonal to each other. So actually, it's an if and only if. Lines corresponding to adjacent vertices are not orthogonal and hence must be in the same part of any decomposition. Yes, okay. Therefore, all the lines in L prime are in the same part. Right, because the graph is connected. Yeah. Gram-Schmidt, communism. Where is Ounce Schmidt? I don't understand the communism statement or question, but where is Ounce Schmidt? Actually, yeah, why are we talking about grams in the first place? Wait, no, grams is what we want. Grams is what we want. Ounce. Wait, do we want grams? Excuse me. Yeah, we want grams. Ounce is nonsense freedom unit BS. And we don't believe in that over here. Any line lying in a star with two other lines. Any line lying in a star with two other lines is not orthogonal to either of them, and therefore lies in the part of any decomposition. In the same part of any decomposition of what? Wait, I thought we were done already. Oh, right. All we were able to say is that the lines in L prime are in the same part. Okay, but then also any line lying in a star with two other lines is not orthogonal to either of them, and therefore lies in the same part of any decomposition of L. What? My brain hurts. You swear I said metric was communism yesterday? Yes, actually, that's true. That's true. I did say that. But I also made no promises to remain consistent on my beliefs and what I vocalize. Metric tensor is the truth. That is true. Oh, 8:56. I gotta go, gang. I gotta go. I gotta tutor someone right away. So, peace out. I'm glad we made progress through half of one lemma, and yeah.